Hello to all. Thank you for being here. My name is Fatama. I'm a first-year PhD student, and I'm going to present an overview of my thesis entitled Climate Optimal Aircraft Trajectory Planning at Network Scale, which is supervised by Manuel Soler. First, I'm going to start with the motivation of this thesis. As my colleague presented, aviation contributes to global warming through the emission of CO2 and non-CO2 effects. And the effect of non-CO2 emission could be mitigated by efficient trajectory optimization to avoid climate hotspot areas. Here we depicted two sets of trajectory. Yeah, the first one is cost optimal one, and the second is climate optimal trajectory. That each individual flight are optimized. That each flight are optimized individually. So there arises a question: is adopting independently climate optimized trajectory operationally feasible? They can fly. The answer is no, because the ATM system, air traffic management system, is a complex system that cannot be characterized by each individual element, but by their collective behavior at network scale. May adopting independently optimized trajectory result in more congested area around climate hotspot like here, which raise some challenges in network scale, such as reducing safety, increasing complexity, and workload, which are not acceptable for ATM system. We need to analyze the effect of considering climate impact at network scale and mitigate the trajectory at this level, which has been identified as a scientific gap. In this respect, the main objective of this thesis is stated in three main parts. At first, identifying the climate hotspot in aerospace and performing trajectory optimization for all individual flights. Here is an overview of optimizing individual trajectories. After obtaining a set of climate optimal trajectory, we need to assess the effect of adopting this optimized trajectory at network scale, mainly in terms of workload, complexity, demand, conflict, and other metrics. After assessment, the third goal is to propose a resolution, a strategy to find a set of trajectory modification to find a set of trajectory that resolve the foster effect of considering climate impact, and the new trajectory be as close as possible to the climate optimal one. To solve this problem, we have considered a scenario, and we will present the result in three parts, as I present in previous slide. At first, we obtain the optimal trajectories. We consider a real network scenario with 1,000 flights. The objective function to optimize this trajectory are the weighted sum of operational cost and climate impact. EI is a weighting parameter that weights the climate impact. The trajectory optimization at this level is solved by direct optimal control and uncertainty quantification. The effect of uncertainty are reflected in the flight trajectory, such as fuel consumption and time, by using ensemble trajectory prediction. Here, the result for two scenarios are depicted. As can be seen, the first one, cost optimal without considering climate impact. The climate hotspot, which are shown by red color map, are crossed. But for the climate optimal trajectory, this area mainly avoided. So after obtaining this set of trajectory, we need to assess the effect of adopting these trajectories. At first, we assess the effect of adopting this trajectory in terms of demand. Here, the results are obtained for at three different times. And as can be seen by considering climate impact, this set of trajectories, the sector contain climate hotspot like the pink one is mostly empty, and its neighbor sector or the demand is increased considerably. As another assessment, we assess the effect of this trajectory on number of conflicts. Here, the results for four sets of trajectory are shown. This is the cost optimal, and this is the climate optimal one. Actually, these three are climate optimal with different weighting coefficient. As can be seen, here are the results for this is the effect of considering climate optimized trajectory in terms of average temperature response. This is the cost, and this is the conflict. Here is the Pareto frontier. As can be seen, by increasing EI, the climate impact is reduced. However, the cost is increased. The assessment in terms of number of conflict show that the number of conflict is increased by 170%, which is quite much. So there is a need to a strategic resolution to resolve this conflict. The error bar in this figure show the effect of uncertainty due to the atmospheric variables such as wind and etc. For the next step, we resolve this, the encounter conflict in the previous slide. We perform an optimization problem based on the objective function is based on conflict and minimum deviation from climate optimal trajectory. Beta is a weighting parameter that weights conflict. Here the results are depicted. As can be seen, by increasing beta, the number of conflict is reduced. Here is the result for this for cost optimal trajectory, and here for climate optimal. As can be seen, for the set of trajectory with less climate impact, the potentiality to reduce conflict is decreased compared to cost optimal one. And for both scenarios, we have a small increase in climate impact and cost. And here the Pareto frontier, obtained Pareto frontier for these three objectives. We can say that including other decision variable to this problem, because we solve this problem based on a speed profile by changing the speed profile of each aircraft. Maybe including other decision variables such as lateral path or altitude would be efficient to that we can solve this conflict more efficiently. Here was the result. The outcome of this study was a journal paper and 2 conference papers. For the next year, I'm going to consider a full 4D trajectory optimization, because the trajectory that have been considered in this case study optimized in just the lateral path was optimized, and we are going to consider full 4D trajectory optimization for both structured aerospace and free route, and then used robust trajectory optimization instead of actually in this study we optimized each flight with in a deterministic manner by the mean value of ensemble members, and then we quantified the effect of uncertainty on flight time and fuel consumption and other variables. We can solve this problem with robust optimization, maybe to have a better performance. Regarding the macro level, we need to explore and propose other metrics to assess the effect of adopting climate optimal trajectories. And for the resolution, we need to consider other decision variables such as lateral path, altitude, departure time, to increase the potentiality to resolve the conflict, and then propose a fast and efficient resolution algorithm based on reinforcement learning to mitigate the effect of adopting climate optimal trajectory. Thanks for your attention.